Hi, it's Papa. I'm going to do a series of videos on the geologic history of Georgia. This will be the first one, and we're going to call it GH1, Geologic History Number 1. And in this series, I'm going to talk about geologically what happened, when it happened, what it looks like, and where do you go to see it, to see what happened, see the remnants of what happened. And so this will be the first one, and we're going to take you back 1 billion years ago to Rodinia, Supercontinent Rodinia. What's a supercontinent? Supercontinent's what happens when all the continents, all the land masses, all the land crust in the world come together to form one giant continent. And this has happened several times during the history of the Earth. I can think of at least 3 times, probably 4. The most recent supercontinent was Pangaea, which rifted apart and started rifting apart maybe 200 million years ago or 250 million years ago. But I'm talking about the one before that, Rodinia, 1 billion years ago, the supercontinent Rodinia. And it began to rift apart. Why did it rift apart? Well, because when a supercontinent covers a huge area of the world, it's, as we talked about before, it's like having the lid on a hot pot that's heated. Because the lid's on there, it's going to get hot and boil much faster and much hotter than if the lid wasn't on there. So the land crust acts like a big lid over the molten mantle. And all that heat begins to buckle up the crust, the land crust of supercontinent Rodinia, pushing it up. All this heat bluster creates a blister in the crust, and the heat creates a hot spot. It's a linear hot spot, as we talked about, miles and miles long. And the crust above this hot spot, this linear hot spot, begins to thin, and eventually it snaps, breaks, and that's called a rift. And where that rift forms, the rift gets bigger and bigger and bigger, and an ocean is created in between the two pieces, or the many pieces of the continent, of the supercontinent. I'll show you a picture from the book. This is the book we're using, and you can find it on Amazon, and I have permission to use it. I'm going to show you pictures of the rifting process. Okay. If I can find them. They're coming, they're coming. I think I've showed you this before. See, there's the hot spot underneath the supercontinent. It's really a linear hot spot, hundreds, maybe thousands of miles long, and it heats up, thins the crust, and then the crust pops. Okay, we already saw that. Now see, here it is. It's busted this land crust in two on a long linear line. It's going to put an ocean in between these pieces of land crust. Okay, so that's what happened with Rodinia supercontinent, when Rodinia supercontinent broke up into lots of smaller continents, and oceans were created in between those continents. The configuration of the Earth today looks kind of like that. It's a bunch of separate continents. They will come back together eventually. I don't think you and I are going to be here to see it, but they will come back together eventually, and that process of coming together to form a supercontinent, breaking apart, that's called the Wilson cycle, and that's constantly going on. Everything runs in cycles in the whole universe. So, now, as this rifting process took place, like I said, you had the long linear hot spot, and that was thousands of miles long. But coming off of that hot spot at a 9-degree angle all along that linear rift were these smaller hot spots. We call them dikes, magma dikes, and they assisted mightily in the job of rifting. And the kind of magma that was contained in these dikes that helped split up Supercontinent Rodinia is called diabase. And so you have all these diabase dikes coming out at 90 degrees angles from the big main linear hot spot. Now, all this happened, this rifting apart of Rodinia happened between about 750 million years ago and 550 million years ago. By 550 million years ago, Rodinia was rifted apart into a lot of other continents. So we have a clue in the form of diabase dikes. Now, there's been so much volcanic tectonic activity associated with the breakup of Rodinia that all those dikes, those diabase dikes, have been metamorphosed long ago, and it's hard to find them. But more recently, Pangaea, the last supercontinent we had, rifted apart, starting about maybe 200 million years ago. It actually began during Triassic, which is 250 million years ago. And those diabase dikes we can find today. You can go right to them. Take your hammer and crack off a piece of this diabase. It's a fabulous rock. I'm going to show you the geologic map that shows you these diabase dikes right now. Now, if you have the book, you can see pieces of the geologic map of Georgia. Here is the geologic map of Georgia, and in the book it's broken down into smaller but more highly magnified or zoomed in on pieces. Excuse me. So here's a piece of the geologic map of Georgia. Now see all these, that thin line there, and that thin line there, and that thin line there, and that thin line there. And there are probably some over here. I can't, it's hard, maybe one right there, it's hard to see. Those are diabase dikes. They are all oriented northwest to southeast, and that is exactly perpendicular to the line of the big linear hotspot that rifted Pangaea apart, which was northeast to southwest. The big linear hotspot that rifted Rodinia also ran from northeast to southwest, and that's going to become a major orientation for everything that comes after that. Okay, not only when Rodinia was rifted apart, not only did you get these diabase dikes in this main linear hotspot that created an ocean, you also got, during that long process, you got pieces of the continent that were broken off. First, they started out, these pieces of the Rodinia supercontinent started out as horsts and grabens, which are, when you stretch the crust, it breaks, and a piece of it goes like that, and you've got a low spot and a high spot up here and up here. The high spots are called horsts. The low spots are called grabens. You could just call them basins if you want to. Those are German words. And so basically you got this situation in Georgia. Here is the mainland. This is after rifting occurred, okay? So the ocean is forming way out here somewhere. Okay. This is the mainland of Georgia. And see, you've got a horst, a graben. This crust was stretched and a piece broke off into this graben or basin. So you had a basin here. And look, over here toward the ocean, the big ocean that was being created, you had a whole piece of land crust, a rift or break completely off and kind of separate from the mainland. That is both of those are very significant, because this horst, after it undergoes some more tectonic processes and geologic processes, is going to become our western Blue Ridge of Georgia, and this piece that rifted off is going to become our Piedmont, Georgia Piedmont. But let's go back. And maybe that's enough for now. Except I need to tell you where you go to see these rifted rocks. When you get these horsts and grabens, these rifting basins formed, material flooded, all kinds of material flooded into them pretty rapidly, because the bottom just dropped out and created this deep basin, and water was in there too, underwater basin, and huge amounts of material were coming off the land, because there weren't any plants at all on the land, no trees, no shrubs, not even any ferns or mosses existed at that time. That was Precambrian time. There were probably mats of blue-green algae in the shallow waters. But anyway, so all this sand, silt, and clay, rocks, pebbles came eroding off the land and dumped into these basins. And you can, in the main kind of rock that came off and filled these basins after it solidified is called Turbidite Sandstone and Metagraywacke. And Turbidite Sandstone and Metagraywacke are just versions of the same thing. Turbidite Sandstone, let's look at it in the book. We've kind of talked about it before, I think. Turbidite Sandstone is, if I can find it, sorry it's taking me so long, but, okay. Oops. Yeah, this is it. Right here. See how you've got a matrix of gray siltstone, sandstone, and it's embedded with all these pebbles of quartz, and the quartz is blue. That's one of the diagnostic signs of this rifting event. Blue quartz, hunks of blue quartz. There's also hunks of white feldspar in it. It's all mixed up size-wise. Turbidite sandstone. So a lot of this turbidite sandstone was dumped into these basins, these rift basins, or rift grabens, as the Germans might say. Another kind of rock that's like a smaller version of turbidite sandstone is Metagraywacke. And then with Metagraywacke or Graywacke, whatever they call it, it's really just turbidite sandstone, and where the pieces, the larger pieces that are embedded in the matrix, they're smaller than the ones in turbidite sandstone. The pieces that are in turbidite sandstone are about the size of Abe Lincoln's head on the penny, plus or minus. But with Metagraywacke or Graywacke, whatever you want to call it, it's Graywacke at first, and then if it gets metamorphosed, it's called Metagraywacke. Anyway, the big pieces embedded in the matrix there are about the size of Honest Abe's ear on the penny. Ow, ow. Okay, where do you go to see this rock? Well, in Georgia, you go to our western Blue Ridge province. Amicalola Falls State Park is there. You can see the rocks there. You can see them at Fort Mountain State Park, which is on the western edge of the western Blue Ridge. But the best place to see them is not in Georgia. It is in Great Smoky Mountains National Park. Great Smoky Mountains National Park is an absolute showcase. It is an ancient rift basin from when Rodinia rifted. It's the rocks there are at least 750 to 550 million years old, and there's basement rock, which is the rock that these that the original crust of Rodinia is 1 billion years old. So go to Great Smoky Mountains National Park and look for this turbidite sandstone and this meta-graywacke. You'll find a lot of other rocks there too, but those are like the showcase, the classic examples of rifting. What happens when you get a rifting situation on a supercontinent? Now, those rocks are all gray, and that tells us something. It tells us, number one, that it was cold. The climate was chilly, cold, not hot and dry, chilly and wet when this rifting occurred. The climate here in Georgia and obviously at the Smokies too, because rhodinium was way down in the southern hemisphere in the high latitudes, maybe latitudes where we are, maybe 30 degrees south latitude, about where we are today, plus or minus 30, 40. That's one reason. So the iron that those rocks are full of was not oxidized. When you get iron, when you get rocks that are laid down and exposed to hot, dry climates, they turn red like all the rocks out west. Well, that's one. This iron in these rocks, these rift rocks, was not oxidized. And another reason, they poured into this underwater graben. Well, the chances for oxidation or rusting there were basically zero. So that's why all these rocks are gray. So when you see a lot of gray rocks, you can tell yourself that the climate was not hot and dry. It was wet. It could have been wet and warm. It could have been wet and cool. So anyway, that's GH1. That's the rifting of Rodinia. The next video in this series, this sub-series about the geologic history of Georgia, is going to be GH2. That will be the taconic mountain building event, the taconic orogeny, where things got tacked on. Anyway, see you next time. Pop out.